Um, I want to start with a little disclaimer. This seminar, of course, has a pure and an applied side. This is a completely pure talk. If there are any practical applications of anything I will say, I will be amazed. Okay. So the topic is equations for unknown CM functions. It's joint work with Kevin Lully. Now let's see why. There, now I'm able to move the slides. Okay, so the talk is about linear equations for unknown CM functions. So here is a linear equation on the top line, a linear equation for unknown functions. Can everybody see my cursor, my arrow moving around?
Yes, we can.
Yes. Okay, great. Okay, so we're given some coefficients. They're functions on Euclidean space Rn. We're given a right-hand side f, a function on Rn. The unknowns are the capital Fs, and we want to know whether this equation, or perhaps the system of such equations, has a solution in which all of these functions belong to Cm. That is, they have m continuous derivatives on Rn. That's the problem. Okay. Now we want these functions to be in Cm for a fixed m, so we're not allowed to lose derivatives. There is a very interesting literature going back to the 1960s allowing discussions of these problems when you're allowed to lose derivatives, but we're not. Okay, the subject actually began with the C0 case, in other words, just continuous functions rather than Cm, and it started in the work of algebraic geometers. And there on the slide are the names of the algebraic geometers: Brenner, Epstein, Hochster, and Kolar. Why should one study such things? Well, there are two different motivations. One comes from Kolar, who asked simply, how can you tell when a rational function on Rn is continuous? Maybe P and Q, the numerator and denominator, have common zeros, in which case it can be a subtle question to decide whether P over Q is a continuous function. And surely we would like to know such things. Of course, if you want to know whether P over Q is continuous, that means that the linear equation QF equals P has a continuous solution F. So that's a particularly simple case of one linear equation for one unknown C0 function. Brenner, Epstein, and Hochster instead had a different motivation. They were interested in different notions of closures of ideals. So given polynomials A1 through AD on Rn, consider the polynomials little f for which our equation, as on the slide, for which our equation admits a continuous solution, capital F1 through capital FD. The little f's for which that can be done form an ideal in the ring of polynomials. By contrast, if you were to demand that the capital F's are also polynomials, then by definition, the little f's are simply the polynomials in the ideal generated by the a's. But if you allow the capital F's to be merely continuous, then you get a bigger ideal, or possibly bigger ideal. That's the closure of the ideal generated by the a's. And so they wanted to know what's with that? How can you compute those? What are they like? And they looked at an interesting example, which we'll return to later. And there it is. It's a particular linear equation for unknown functions, capital F1, capital F2, and capital F3 of three variables. Okay, so that's the motivation. Well, all right, so what are the particular questions? There are three of them. So throughout this talk, little m, little n, and capital D are fixed positive integers, and their significance is that we're looking at functions, we're looking at D functions on R little n, each of which has m continuous derivatives. And so given functions capital A1 through capital AD and little f on Rn, maybe they're polynomials, maybe they aren't. Our first question is simply, how can we decide whether there exist Cm functions that satisfy the equation? Oh, I should have said, even though I guess people's YouTube, Zooms are muted. Please, this talk is intended to snow nobody. So please, if you have any questions, just stop me. Okay, that was the first question. Second question is the following. So we fix our usual positive integers m and d. Capital A1 to capital AD are now definitely polynomials. Before they might or might not be, but now they are polynomials. And we look at the polynomials little f for which our linear equation has a CM solution. So those little f's form an ideal. That's the closure that the algebraic geometers defined, at least in the C0 case. And the question now is, exhibit generators. Given the capital A's, how can you compute generators for this ideal of little f's? Okay, that's the second question. The third question has to do with what you can say about the solutions, if there are any. So we fix our usual m, n, and d, and we're given our usual A's and F's, and they are polynomials now. And we suppose that our linear equation for the capital F's has a CM solution. Then what kind of functions, what kind of CM functions might these capital F's be? Can we take them to be, for example, rational functions? Turns out the answer is no. Can we take them to be semi-algebraic functions? The answer is we'll see, but the bottom line is we don't know. Let me just recall the definition of semi-algebraic sets and functions for a minute. So a semi-algebraic set is a union of finitely many sets of the form on the slide. Maybe there's too much written on the slide. Each one of these sets is the set where some polynomials are positive and some other polynomials are zero. And so that means that you can decide whether an arbitrary given point belongs to our set E by looking at the values of finitely many predetermined polynomials applied to that point. So that's a semi-algebraic set, and a map from a semi-algebraic set into a Euclidean space is called a semi-algebraic map if its graph, the set of all points x, y, for which x is in E and phi of x is in Y. If that graph is a semi-algebraic set, the map is called semi-algebraic. And so semi-algebraic functions are functions given essentially by elementary formulas. And so we want to know if there's a CM solution to one of our equations, and if the coefficients on the right-hand side are polynomials, can we at least take our solution to be semi-algebraic? And we don't know. So I'm going to show you an answer, or part of an answer anyway, to questions 1 and 2. And regarding question 3, we have only some partial results, rather weak ones. Okay, algebraic geometry. I'm not an algebraic geometer. How I came to get involved is a cute story. So I was minding my own business one day when I got an email from my colleague, the distinguished algebraic geometer Janos Kolar. And he asked me, do I know anything about these problems? He sent me an email. He described the problems. Do I know anything? And immediately I answered, no, I know nothing about this, of course. But then I started thinking, and to my great surprise, it turns out that the answer is yes, I actually did know something about it because, well, I'll get to the reason in a minute. But as a result of that exchange, there is a joint paper by Kolar and me giving 2 independent solutions of the first question, namely, how can you tell whether a solution exists, in the C0 case. So if the functions are required to be merely continuous rather than having m continuous derivatives, then there are 2 completely different solutions, one by Kolar using algebraic geometry that I wish I understood, and the other by me using only analysis. Okay, now, all right, so how did it happen that in fact I did know something about these problems? And the answer is that the algebraic geometry problems turned out to be very closely related to a problem that I had already, at the time, spent years thinking about. And it is Whitney's extension problem. So I think the next thing I should do is say what Whitney's extension problem is. So we now fix positive integers little m and little n. We're given a compact set E in Rn. Well, it's compact, but it's otherwise arbitrary, so it might be just awful. And we're given a function phi, a real valued function on E. And Whitney's problem is, how can one decide whether there is a CM function on Rn which extends little phi from E to the whole Rn, as shown on the slide. Okay, so which functions phi on our awful set E are restrictions of CM functions to E? Okay, so we now have two very different sounding questions. They both involve CM, but they otherwise sound as if they have nothing to do with each other. One of them is Whitney's extension problem, and the other is the existence of solutions to one linear equation, or more generally, many linear equations for unknown CM functions. And it turns out that these two questions are both special cases of a question about something that I call bundles. These are not, pardon me, the bundles in this lecture are not going to be the usual bundles in, let's say, differential geometry or topology. They will be sort of vaguely similar, but they're not at all the same. And one has to talk about bundles in order to solve either of these two questions, and so they are different special cases of the same thing. So the plan of the rest of the talk is that I'm going to define bundles, fibers, subbundles, and sections of bundles. Okay. And then I will pose what I'll call the main question on bundles, and I'll explain its solution in terms of a construction called Glaser refinement. And that's going to solve question 1 from the Brenner, Epstein, Hochster, Kolar theory, the first of the algebraic geometry questions. If time permits, I'll discuss the solution of question 2, and it's very unlikely that I'll get to say anything about question 3, and maybe that's just as well because I don't know the answer. Okay, so we're preparing to define bundles. Now, unfortunately, I have to prepare to define bundles. So there will be a few slides of notation, and then we'll get to the definition of bundles, and then we'll see what they're good for. So we fix our usual positive integers m, n, and d. Script p is going to be the vector space of polynomials of degree at most m on Rn. And we think of a polynomial in script p as the Taylor polynomial of a CM function at some given point x. And so Jx of f, J for jet, the mjet, Jx of f is the mth degree Taylor polynomial of a function f at x. So Jx is then an element of script p. Okay, that's the beginning of the notation. Okay, now we're also going to talk about vector valued functions because our linear equations involve d scalar valued functions. We can think of them as a single vector valued function. And so Cm of Rn Rd is the space of all Rd valued Cm functions as on the slide. So a single f with an arrow on top consists of d different scalar valued Cm functions on Rn. And the jet of such a thing is defined just component wise as on the slide. Okay, so so far we're taking Taylor polynomials at points x of CM functions or vector valued CM functions. Okay, now I've got to talk about jet multiplication. So if you have two polynomials of script in script p, each of them is a polynomial, let's say, of degree m. When you multiply them together in the obvious way, it's a polynomial of degree 2m. But if you take the Taylor polynomial of that product at a given point x, that is the jet product at x, and so it is again a polynomial of degree at most m. And the significance of that is that if you look at the product of two smooth functions and you take the Taylor polynomial of the product, it is the product of the Taylor polynomials with respect to this funny multiplication that I call dot sub x. And so if you look at the polynomial script p with that multiplication, r dot sub x, that's a ring. R sub x, that's the ring of m jets at x. So if you like, it's just the ring of CM functions in which you identify two functions if they agree to order m. Okay? So this is a simple finite dimensional ring. As x varies, of course, these rings are all isomorphic, but they're not identical, and it's useful to remember the label x. Okay? That's the notation so far. And because we are looking at d different functions, it's useful to look at a direct sum of d copies of this ring. So I write it Rx to the d. Elements of that are then vectors of polynomials P1 through PD. Each of those P sub j is a polynomial of degree at most m. And of course, one can multiply such a vector-valued polynomial by a scalar-valued polynomial just component-wise. And so that means that Rx to the power d is an Rx module. We have things that we can multiply by elements of a ring. And all of that reminds me of the last time I actually passed an exam on algebra, which was, I think, in 1967. So you'll see concrete uses of these things. Anyway, so that's an RDX. I'm sorry. So Rx to the D is an Rx module, and we're going to be looking at Rx submodules. We'll see concrete examples in a few minutes to make this seem less ridiculous. And I want to make a significant small point, which is that the following degenerate cases are allowed. First of all, you can take the whole of Rx to the D, and that's allowed to be a submodule. You can also take 0, and we're going to allow that as a submodule, and those are sort of conventional degenerate cases. But I'm going to allow also the empty set, and I'm going to declare that the empty set is acceptable as a submodule. And that you'll see why. Okay. So that was the notation. Okay. Now with that notation, I can tell you what a bundle is, a fiber, a subbundle, and a section. Okay. Suppose that E is a compact subset of Rn. A bundle is a family parametrized by the points of E. And for a given point x in E, the object in the family, the hx, is a translate or a coset of an Rx submodule. So for each point x in E, the fiber, it will soon be called a fiber, hx, is simply the submodule I sub x translated by f sub x. And I sub x is a submodule of Rx to the D. So it's closed under multiplication by jets in the ring Rx. Okay. Note that any particular hx might be empty because we allowed the empty set as an Rx submodule. So a bundle, all right, this bundle consists of a bunch of h sub x's, and any particular hx might actually be empty. And that sounds ridiculous, but in fact, it's important. Okay. All right, well, if we're given a bundle like that, then the set E is called the base, and hx is called the fiber of the bundle at x. I think that's sort of natural terminology. Notice, however, unlike bundles in geometry, I've assumed absolutely nothing about how hx depends on x. The dimension of hx as an affine space as a function of the point x may or may not be measurable. I don't care. Okay, so it's completely arbitrary. All right, subbundles. Suppose that you have two bundles over the same base. So here they're called H and H tilde. Okay, H tilde is a subbundle of H, and it means simply that at each point x in E, the fiber of H tilde is contained in the fiber of H. And we simply write H contains H tilde as on the slide to denote that. So now we've defined bundles, subbundles, fibers, bases. I haven't yet defined sections. I'm going to do that now. So suppose we have a bundle and we have a CM function with values in RD. Then F is called a section of the bundle if and only if at each point of E, the Taylor polynomial of F, or the jet of F, at X belongs to the fiber HX. Okay, that's what a section means. Now, all right, a lot of some notation and some definitions. Is it clear? Any questions? Okay. Okay, now the main question about bundles is simple to state. Given a bundle, please decide whether it has a section. Trivial remark. If our bundle has even one empty fiber, of course it has no sections, right? A section is a function whose jet at every point belongs to the fiber. And if one of the fibers is empty, there's not a chance for the jet of the function to belong to it. So H had better have only non-empty fibers. Okay. Now, the reason for all this language is that both the Whitney extension problem and the first of our algebraic geometry problems are special cases of the main question about bundles. Furthermore, you actually can't answer either the Whitney extension problem or the algebraic geometry problem without generalizing them out of their original framework and into the framework of bundles, or at least if it is possible, I haven't the vaguest idea how. Okay, let's just see why both the Whitney problem and the algebraic geometry problem are special cases of the question about bundles. Okay, so let's return to the Whitney problem. So given a function phi on a compact set E, is there a function in Cm that agrees with phi on E? That's Whitney's problem. Well, I'm going to set up a bundle. For each point x in E, let h of x be the set of all polynomials whose value at x is the value of the given function phi at x. That's a bundle. And a section of that bundle is precisely a function f in Cm that agrees with phi on E. And that follows just from chasing down the definitions. There's nothing remotely deep about that. So that means that there is a Cm function that extends phi if and only if that particular bundle has a section. Okay, and our main question asks, given a bundle, decide whether it has a section. So if we can answer the main question on bundles, we can answer Whitney's problem. Let's look at the first of the algebraic geometry problems. Are there Cm functions f1 through fd that satisfy some linear equation as on the slide? Well, for each point x in Rn, define h of x to be the set of vectors of polynomials that satisfy the linear equation just at the single point x. Then if you assemble all of those into a family script h, the family of all h sub x's, that's a bundle, and a section of script h is precisely a function, a vector-valued function where all the components are in Cm in such a way that the linear equation is true everywhere. And so that means that the algebraic geometry problem, at least question 1, is also a special case of the main question about bundles. And that's what this slide says. Okay, we've cheated. Rn, our base, isn't compact. And a few slides ago, I said that a bundle is defined over a compact set. So this is a cheat, but it's a minor cheat. This technical problem is trivially overcome. I don't want to bother with it. Let's just agree. Okay. So if we can solve the main problem about bundles, we can solve the algebraic geometry problem, and we can solve Whitney's problem. Okay, so we've defined bundles, we've posed the main problem, we've seen that the Whitney extension problem and the algebraic geometry problem are special cases. Now that's all very nice, but we've got to solve the main problem about bundles. Okay, so we're going to do that next. And again, this is joint work with Kevin Lully, but we didn't invent it completely out of the blue. We built it on decades of previous work, going back to Whitney, also to Georges Glaser, pardon my mispronunciation of French, which I guess in this case is also a mispronunciation of German. Glaser was a French mathematician active in the 50s. Yuri Brudny and Pavel Schwarzman, originally from the Soviet Union, now long ago from Israel. Ed Bierstone, Pierre Millman, and Wiesław Pawluski, and pardon my pronunciation of Polish. Okay. All right. So our question is, how can we tell whether a given bundle has a section? In order to answer the main question, we need a definition, and that's Glaser refinement. Okay. Given a bundle, we're going to define its Glaser refinement, which is another bundle over the same base. And so if the bundle is denoted by script H, the Glaser refinement is going to be denoted for the moment by script H tilde. Okay, now later in the talk, I'll actually define Glaser refinement, but I propose now to skip the definition and just tell you a couple of good properties of the Glaser refinement. Later, when I give the definition, I will check that the good properties are true, but I think the discussion flows better if I give you the key properties now and the definition later. Okay, so the key properties of H tilde are the following. The Glaser refinement is a subbundle of the bundle that you started with. However, and so that means in principle that H tilde might have fewer sections. Remember, a section of a bundle is a function or vector valued function whose jet at each point belongs to the fiber of the bundle. Well, if the fiber is smaller, there are fewer chances for the jet to belong. And so one could think that because H tilde is a subbundle of H, that it has fewer sections. But in fact, H tilde is carefully defined so that H and H tilde have exactly the same sections. And furthermore, H tilde can be computed from H by doing linear algebra in some fixed dimension and then taking some limit. Okay, so if we want to know whether H has a section, we may as well ask whether H tilde has a section. And so we have passed from a bundle to its Glaser refinement H tilde by discarding junk. Junk means elements of fibers that could never ever arise as the jet of a section. All right, notice that even if, well, notice, I mean, I haven't defined the Glaser refinement, so I don't know how you could notice it, but even if all the fibers of the original bundle are non-empty, it might happen that the Glaser refinement has some empty fibers. In that case, the Glaser refinement obviously has no sections. And since H and H tilde have the same sections, that means that the original bundle H has no sections. Okay, so it can happen that all the fibers of our bundle are non-empty, and yet there are no sections because the Glaser refinement has some empty fibers. Well, turns out that you have to iterate that construction. So we're going to talk about iterated Glaser refinement. So given a bundle H, I'm going to call it the zeroth Glaser, its own zeroth Glaser refinement, H0, but then H1 is defined as the Glaser refinement of H0, and then H2 is defined as the Glaser refinement of H1, and so on. And so we get a descending chain of bundles. These bundles are all computable because each one can be computed from the previous one. And for each L, the sections of that iterated Glaser refinement HL are the same as the sections of H because Glaser refinement preserves sections. Okay, the process stabilizes. That's an ingenious but elementary lemma going back to Glaser essentially. So from some point on, if you keep Glaser refining, you don't get anything new. There's some L star depending only on our basic integers m, n, and d, so that from the L star iterated Glaser refinement on, they're all the same. So there's no point Glaser refining beyond stage L star. Okay. So except for the embarrassing fact that we have not defined the Glaser refinement, we can talk about HL star, and we can use that to answer the main question on bundles. And the answer is actually quite simple. Let H and H sub L star be as above, then H has a section if and only if H L star has no empty fibers. We've seen that if any iterated Glaser refinement has even one empty fiber, that's a fatal obstruction and H cannot have a section. But the theorem says that that's the only obstruction. So if by the time you get to the L starth iterated Glaser refinement, and if you see that none of the fibers is empty, then our bundle has a section. Okay. All right. So we've answered the main question on bundles, except that we haven't defined the Glaser refinement. All right, so let's define the Glaser refinement over the next few slides. So now, where do we stand in the talk? How do I stand with respect to time? Oh, I've got more time than I thought I would have. That's great. Am I right that talk should be maybe 50 minutes or so?
Yes, but you can take as long as you want.
Oh, okay, thanks. So, okay. So, all right, we have some algebraic geometry questions, questions 1, 2, and 3. We have Whitney's extension problem. We've seen that Whitney's extension problem and the first of the algebraic geometry questions are both special cases of a problem about bundles. We've given some definitions, and modulo those definitions, we've stated a theorem that answers the main question about bundles, and therefore lets us answer the first algebraic geometry question and Whitney's extension problem. Okay, but we haven't defined Glaser refinement, so let's do that. Okay, so let me first give one slide of motivation. So here's the motivation. Suppose we have a CM function on Rn, and suppose we have a point x0 in Rn. All right, so here we have an epsilon and delta. Given epsilon, there is a delta such that what? Given any 2 points within distance delta of the point x0, if you compare the Taylor polynomial of f at x with the Taylor polynomial at y, they are very close in the sense that the estimate holds, the estimate on the slide holds. There's a little trivial point, which is that this, let's see, among the cases covered by this inequality are the case in which x and y are the same, and the multi-index alpha has full order m, in which case the right-hand side is epsilon times 0 to the 0. And so we need a little convention. 0 to the 0 for purposes of this slide is 0. So that's the inequality, and it's just Taylor's theorem in slightly fancy language, because I'm talking about Jx and Jy. But if you think about what it means, it's just Taylor's theorem. And of course, if 2 points are very close together, and you look at the derivatives or you look at the Taylor polynomials of a nice function at those points, of course, they're going to be very close together. How close? This close. Okay, so that's the motivation, and it's just Taylor's theorem. Okay, so now I'm going to define the Glaser refinement based on that motivation. So we're going to fix a large enough integer constant called k. It's determined by our usual m, n, and d. Okay, and so here on this slide and the next are the definition of the Glaser refinement. So suppose we're given a bundle, script h. The fiber at x is hx. What is the Glaser refinement? Well, it's the bundle h tilde with fibers h tilde sub x, and so I have to tell you what the h tilde sub x are, and that will define h tilde. So for each point x0 in E, h tilde of h tilde at x0 is the following. It consists of all the p0 belonging to the fiber of the original bundle at x0, such that for all epsilon there exists a delta such that the condition in the box holds. So let's look at that. Well, there are k points instead of just 1 or 2 extra, but for any k points of E which are within distance delta of x0, I can pick polynomials p1 belonging to the fiber of h at x1, and p2 belonging to the fiber at x2, and so on, pk belonging to the fiber at xk, and they satisfy an inequality that looks familiar from a couple of slides ago. Okay, so that's the definition of the Glaser refinement. And I think it is, I mean, I hope that every single slide is painless. Maybe this is the least painless of the slides in the talk. Notice that P0 through P1, I'm sorry, P0 through PK are all allowed for purposes of this inequality. This inequality is supposed to be to connect Pi to Pj, where I and j run from 0 through k. However, P0 plays a different role from P1 through Pk. P0 is fixed, and we want to know whether it belongs to H tilde sub x0. So P0 is fixed, and for each x1 through xk sufficiently close to x0, we have to produce P1 through pk. So that's what I tried to say in fewer words on the next slide. P0 through pk all appear in the definition and in particular in the inequality, but P0 stays fixed while P1 through pk vary. Okay, that's the definition of the Glaser refinement, and it's not entirely painless, but there it is. Okay, well, so we've defined the Glaser refinement. Now let's check the key properties that it's supposed to have. So the first key property was that H tilde, the Glaser refinement, is a subbundle of H. And that's obvious. Given a bundle H, remember the Glaser refinement H tilde was defined as follows. The fiber of H tilde consists of all elements of the fiber of H such that blah, blah, blah. Well, all right, so obviously the fiber of H tilde is contained in the fiber of H. And so that means H tilde is, of course, a subbundle of H. Okay, that wasn't rocket science. All right, let's look at key property 2. That's a little more interesting. So H and H tilde have the same sections. Okay, well, since H tilde is a subbundle of H, every section of H tilde is automatically a section of H. The thing that requires proof is that every section of H is also a section of H tilde. Okay, so suppose that F is a section of H. So that means that F is a CM function, and its jet at X belongs to the fiber HX for every X in E. What we've now got to show is that the jet at X0 of F belongs to the fiber H tilde of X0 for all X0 in E. Well, that means we've got to show this inequality in the box. So given epsilon, there exists a delta such that for every X1 through XK in E within distance delta of X0, we can find polynomials P1 in HX1 through PK in HXK, satisfying the usual inequality, which I've written again. So here P0 is the jet of F at X0. That's what we have to prove. Well, to show that, all right, we've got to find P1 through PK. We simply set each Pj equal to the jet of F at the point Xj. And that works. P1 belongs to HX1 and so on. PK belongs to HXK because F is a section of H. And so its jet at every point belongs to the fiber of H. How about the inequality, the derivatives of Pi minus Pj evaluated at Xj are supposed to be small as shown on the slide? Well, that's just Taylor's theorem. That's why I had the previous slide with motivation. So these P's are now jets, Taylor polynomials of F at nearby points. And so, of course, they're close together. And Taylor's theorem gives us what we want. That's why the definition is phrased the way it is, precisely so that this argument would work. So we've proven key property 2. We've proven that a bundle and its Glaser refinement have the same sections. How about key property 3? So the Glaser refinement can be computed from the original bundle. Well, given a bundle, the usual notation, script H consisting of fibers H sub X, given points X0, X1 through XK in E, and given polynomials P0, P1 through PK, each of which is of degree most M, we define Q of the P's and the X's as on the slide. Okay, those things that look like either vertical bars or parentheses should be vertical bars. These P's are vector valued, so that's a norm squared. Okay. So look at that thing. Well, it is a quadratic form in the P's once you fix the X's. Okay, and I'm going to define script Q of P0 and the X's to be the minimum of the Roman Q, where I allow P1 to vary in the fiber at X1 and P2 to vary in the fiber at X2 and so on. pk to vary through the fiber in at xk. So script q is the minimum of a positive semi-definite quadratic form on an affine space. And so we can compute it by linear algebra. And a given P0 belonging to the fiber of the original bundle belongs to the fiber of the Glaser refinement if and only if script q tends to 0, as shown on the slide. Okay, and well, I wonder how it feels to be on the receiving end of this lecture. Maybe you have to remember some definitions, but the content of this remark, the proof of this remark consists of remembering the definitions. There's nothing more to it than that. So we can decide this by doing linear algebra in fixed dimension in order to compute script q, and then taking a limit. And so if you believe all that, we have defined the Glaser refinement. We have checked its 3 key properties. It's a subbundle. It has the same sections, and we can compute it. And we've used it to answer the question, how can we decide whether a given bundle has a section? One thing we haven't done is to discuss the proof of the assertion that that we've answered the main question on bundles. Okay, so why is it that a bundle has a section if and only if a suitable iterated Glaser refinement has no empty fibers? That's a long, hard proof. I propose that we just skip it. Okay, so all right. So we're done with question 1, and there's time remaining. So let's look at question 2. So let me remind you, we're now given a list of polynomials, and we're interested in all those polynomials, little f, that are expressible in the form of the usual linear combination a1 f1 plus blah blah ad fd, where the capital F's are Cm functions on Rn. So that's an ideal in the ring of polynomials on Rn, and our problem is to exhibit generators for that ideal. Okay. Well, again, the results I'm going to talk about are joint work with Kevin Lully. Okay, let me start with a little observation with bad news. I think this is part of what makes the problem interesting. We can't solve this problem by analysis alone because it's about an ideal in a polynomial ring. On the other hand, we can't solve this problem by algebra alone because it's about Cm functions. So what we're going to do is to make a clean splitting into a problem which is almost entirely about analysis and a problem which is absolutely entirely about algebra. Okay, so I'd like to explain to you what the analysis problem is and what the algebra problem is. Okay, so here's the analysis problem. We're given our list of polynomials, but our little f is not yet a polynomial. It's just a C infinity function. And we want to characterize the C infinity functions for which our equation has a Cm solution. That's the analysis problem. Let's go back to the example of Brenner, Epstein, Hochster, and Kolar. So here's our equation for functions in 3 variables, and our little f is now C infinity. And we would like to know whether there is a solution to this equation in which the capital F's are continuous functions, C0 functions. And I apologize, there's a mistake on the slide. So a continuous function exists if and only if the stuff in the box is true. And there's one other thing that I should also have said, which is that the mixed partial just with respect to y and z of little f, without the extra partial x, that also vanishes at the origin, x equals y equals z equals 0. So except for that typo, the continuous solution exists if and only if the conditions in the box are satisfied. And that's an exercise, which I won't do. Okay. However, notice something interesting. We are posing a problem about existence of continuous solutions. The capital F's are merely supposed to be continuous, but the necessary and sufficient conditions on little f involve derivatives of little f up to order 3. Okay. Well, so here's the solution to the analysis problem in the general case, not just for the example of Brenner, Epstein, Hochster, and Kolar. So suppose we're given polynomials P, A1 through AD. Then there exists a finite list of linear differential operators that I'll call L1 through LK with three properties. I'm going to call the three properties A, B, and C, just because each one gets a slide to itself. Property A just tells you the form of the differential operators. So each of our differential operators has the form shown on the box. So it's just a linear partial differential operator, but there are two interesting things about it. One is that it may be a higher order differential operator than you might expect. We're now looking for CM solutions, but the order of our differential operator might be more than M, as it was in the example of Brenner et al. Okay, and furthermore, the coefficients are not necessarily smooth or continuous functions the way they usually are in PDE. They are instead semi-algebraic functions, in particular, possibly discontinuous. So these operators act on C infinity functions, and they produce possibly discontinuous functions. Okay, that's property A. That's simply the form of the operators. Now, what do these operators do? And the most significant part maybe is property B. Our equation, the usual equation, in the case that little f is a C infinity function, has a CM solution if and only if our function little f is annihilated by each of those differential operators. Okay, and the last property, property C, is that the coefficients of all of those operators can be computed. Remember, I said that the first problem, the analysis problem, was 99% analysis. The 1% that isn't analysis, that's algebra or something, is this property C, and simply the proof of properties A and B is constructive, and at each step along the way, you can compute everything, and that's why property C happens. Okay. Let's see what that means in our usual example, the Brenner, Epstein, Hofstadter, Kolar example. So there's the equation yet again at the top of the page, and the relevant differential operators are the following. These fancy ones are indicator functions. So we have the indicator function of the multiplying the identity differential operator, and the indicator function of the z-axis times partial with respect to x, and the indicator function times partial y, and the indicator function of the origin of this third order guy, and the one I forgot, the indicator function of the origin times the mixed partial with respect to y and z. So for little f to be annihilated by those is precisely the same as, let's go back. Those conditions, okay? So for example, f equals 0 at on the z-axis. Well, that means that the indicator function of the z-axis times 0 derivatives applied to f vanishes. So we've this solution in the general case includes the example. Okay. All right. Now the proof of the proof of that result, the proof that there are such differential operators, is based on further study of Glaser refinements. And again, I hope that this is going to be a nice, pleasant talk without heavy duty demands on you. And so let's just take it for granted that works. Now, I said that the algebraic geometry question 2 breaks up into an analysis problem and an algebra problem. Here's the algebra problem. Suppose we're given a list of differential operators with semi-algebraic coefficients. So in the same format as I just discussed, but not necessarily the L's arising from the analysis problem, just any list of linear differential operators with semi-algebraic coefficients. Well, then I'd like to use those to define a polynomial ring, and it is the following. So it consists of all polynomials which are not only annihilated by all the differential operators, but have the property that if you multiply them by anything, the product remains annihilated by all the differential operators. Okay, so that's obviously an ideal, because I mean that's why I threw in this arbitrary Q to make it obviously an ideal. And so that's the ideal I of L1 through L nu max. The problem of computational algebra is, given a list of such differential operators, exhibit generators for that ideal. Let's see. Notice, for example, let's say that L is simply the indicator function of a set, of a semi-algebraic set, times no derivatives, so times the identity operator. Okay. In that case, what is annihilated by that? Well, functions that vanish on the given semi-algebraic set. And so this problem of computational algebra includes, as a little special case, given a semi-algebraic set, compute generators for the ideal of all polynomials that vanish on that set. Okay, but this is more general because there are some differential operators floating around. So the problem is to exhibit generators for that ideal. Okay, notice that if the set of polynomials annihilated by the differential operators already form an ideal, then that ideal is I of L1 through L nu max, right? The fact that I demanded that not only should P be annihilated, but Q times P should be annihilated for every Q. That doesn't matter if the P is annihilated by the differential operators already form an ideal. Okay, so if we can solve that problem of computational algebra, we can then read off generators for the ideal of polynomials for which our linear equation admits a CM solution. Let's run through the simple steps. So suppose that little f is a polynomial. Well, in particular, it's C infinity. So we can solve our equation with the CM solution if and only if our f is annihilated by all these polynomials. Aha, but it's clear that that the polynomials for which there is a CM solution already form an ideal. And so, right, that's why the algebraic geometers were interested in question 2. And so therefore, it's equivalent to say that Q times F is annihilated by the differential operators for all Q. And that, by definition, means that F is in this ideal. So, okay, so if F is a polynomial, then there is a CM solution if and only if F belongs to this ideal that I called I of L1 through L blah, blah, blah. And the computational algebra problem is precisely to find generators of that. And so we have solved problem 2 because Kevin and I worked out an algorithm, absurdly inefficient, but an algorithm that terminates in finite time to compute generators for this I. Okay, so that's question 2. And let's see, question 3. I think I would rather allow time for questions rather than say anything about question 3, except to tell you that it's a special case of some more general question about bundles, and Kevin and I proved the thing about bundles in dimension 2, and we're stuck there. So all right, so let's zip through. Oh, I should say, however, that Kolar, I mean, I've described the further directions I've gone from the joint paper with Kolar. Kolar has also gone in various directions from that joint paper, and in particular, a joint paper of Kolar and Novak shows that one cannot, in general, take our solutions to be CM rational functions. So the conjecture is that we can take them to be semi-algebraic, and they prove that. Kolar and Novak prove that for C0, but not for CM, and neither do we. And so there's some more general version for bundles, and Kevin and I can prove it, and thank you for listening.